Good morning. Okay, so all right, good morning. So please let me know if you can watch this stream and if you can hear me. Hi Jiva, hi Netaji. Yeah, good morning. So please tell me if my voice is clear. Hi, yeah, Sarvana Priya. Okay, all right. So let's begin. Today we are going to talk a lot of theory. All right. So we always talk theory, but today we are going to do lots and lots of derivations on rotational motion. So let's begin. So let's recall what we studied in last class. In last class, we studied that if we have a body, a particle revolving in a circle, a fixed circle whose axis, whose center lies on, let's suppose, this axis. This axis is perpendicular to the plane of revolution of this particle and it passes through this center. So let's call this z axis. Okay, m is its mass, v is its velocity. Then we had defined two new quantities. So first one is angular momentum. We call it L bar and it is R bar cross P bar. Okay, and this is also called as moment of linear momentum. So R bar is position vector of this mass with respect to this center, and P bar is its momentum, linear momentum, which is m multiplied by v bar. Okay, then so we found that for rotational motion, this is an analog of momentum. Okay, so just like we have momentum in case of linear motion, in rotational motion, or if we talk about this body, this particle revolving in a circle, so in circular motion, angular momentum is an analog of the linear momentum. And we also define a quantity, torque, acting on this mass. So tau equals to R bar crossed with F bar. Suppose there is force F acting on this body. So torque is R bar crossed F bar, and since it is R times F, it is known as the moment of force. Okay, this is moment of linear momentum, the angular momentum, and torque tau is moment of force. And we had found that for this particle revolving in a circle, for the single particle, the relation between this tau and L is just like the relation between F and P. So tau bar is dl bar by dt. Okay, so just like in linear case we have F bar equals to dp bar by dt. This is Newton's second law of motion. So rate of change of momentum with respect to time is equal to the external force acting on the body. So just like this, we have rate of change of angular momentum with respect to time equals to the external torque acting on this body, which is performing, let's say, if we talk about a single particle, then it's performing circular motion. And if we talk about rigid body, we are yet to prove this, but if we talk about rigid body performing rotational motion, then torque is equal to dl bar by dt. So now we will take it from this single particle to the case of rigid body, and we will prove it for the case of rigid body. Alright, so is that clear? Okay, so now let's consider a rigid body. I will write here. Let's suppose we have this rigid body of any shape which is rotating about this fixed axis, and there are n number of particles within this body. So when this body rotates, all particles within the body, they perform circular motion. So let's fix some point and let's call it an origin. So I'm going to denote the position vectors of all particles within this body with respect to this origin. Okay. So now let's consider a particle. So if I consider a particle over here, it is moving in this circle. It is performing circular motion. Okay. And center of the circle lies, let's say, at this point. So this will be its position vector. Okay, this is, let's call it particle number 1. So m1 is its mass, and its position vector with respect to this origin is r1 bar. And I am going to now resolve this position vector along two components. So these are those two components. One is along the axis of rotation, let's call it z axis, and one is perpendicular to the axis of rotation. So the component along the axis, I will call it, let's say, rz. Okay, and because it is position vector of first particle, let's call it r1z. So I am calling this vector r1z bar, and this perpendicular vector, okay, I will call it r1 perpendicular bar. Alright, so I can write r1 bar equals to r1z bar plus r1 perpendicular bar. Okay, and then now I want to find out the torque acting on this rigid body. Alright, so I will erase this part. Okay, thanks Netaji, and hi Kartika. Okay, so now what I want to do is I want to find out torque acting on this rigid body. Okay, so let's suppose this particle, first particle, there are n number of particles. So this first particle, it is moving with some angular momentum. Okay, so let's say p bar is its linear momentum, which is m times v bar. So at the moment, the velocity of this particle will be directed along tangent to this circle. So p equals to m times v1 bar. Okay, so suppose L1 bar is the angular momentum of first particle. So L1 bar can be written as R1 bar cross P1 bar. Okay, then similarly I can write L2 bar equals to R2 bar cross P2 bar. So if we have second particle, let's say somewhere here, it is moving in this circle, it performs circular motion. Okay, and its center lies over here, so its position vector will be this one, a vector directed from this origin to the position of this particle. All right, so this is the position vector. So if this is second particle, its mass is m2, this is r2 bar, and its linear momentum is this one. Okay, it is directed in this direction as that of its velocity. So r2 cross p2. Okay, it is its linear momentum. All right, and similarly we can write, sorry, it is its angular momentum, and similarly we can write the angular momenta of all n particles within the body. So angular momentum of nth particle is Rn bar crossed Tn bar. Okay, then now let's suppose, okay, so what will be total angular momentum of the body? So the total angular momentum is sum of all these angular momenta, L1 bar plus L2 bar plus so on and so forth up to plus Ln bar. So the total angular momentum let's call it L bar. It is L1 bar plus small L2 bar plus so on and so forth up to plus Ln bar. Okay, and then now what will be the torque acting on body? So the torque acting on body tau is dl bar by dt. Okay, it is rate of change of angular momentum with respect to time. And what is angular momentum? It is L1 bar plus L2 bar. So it is sum of angular momenta of all particles within the body. And this can be written in compact form like this: summation of Li. Okay, Li is angular momentum of ith particle. So summation I goes from 1 to n of Li bar. All right. So the torque acting on body can be written as dl bar by dt. And what will be dl bar by dt? So it is equal to, I can say, if I write L bar as summation of this Li bar, then dl bar by dt will be summation I goes from 1 to n derivative of Li bar with respect to the time. Okay, so we just have taken this formula and we have taken derivative. Here we are taking derivative of left hand side and right hand side with respect to time. Okay, so is it clear till this point? Yes. All right. Then next what we'll do is we'll write this dl bar by dt as torque. Okay, so let us erase this once again. Our board is small. Okay, so this can be written as, so dl bar by dt can be written as dl1 bar by dt plus dl2 by dt plus so on and so forth up to plus dln by dt. Okay, and in compact form we could just write it is summation I goes from 1 to n of this term. Okay, so now what is this thing? So rate of change of angular momentum with respect to time for first particle will be the torque acting on the first particle. Okay, so this is equal to what? Torque acting on first particle, on let's say first particle, plus this is rate of change of angular momentum with respect to time of second particle, so this is torque acting on second particle, plus so on and so forth up to plus this term can be written as torque acting on nth particle. And let's not forget these bars because torque is a vector quantity. So now torque can be written as what? So we saw in last class torque is R cross F. Okay, so this is R bar crossed with F bar. So for first particle it will be R1 cross F1 bar, plus for second particle it will be R2 bar cross F2 bar, plus so on and so forth up to plus for nth particle it is Rn bar cross Fn bar. Okay, so we have just written torque as the cross product of position vector of particle and the force acting on particle, each and every particle. Okay, so for first particle it is R1 bar cross F1 bar, for second one R2 bar cross F2 bar, plus so on and so forth up to plus for nth particle the torque acting on the particle it is Rn bar cross Fn bar. Okay, so then now here comes the crucial point, and the crucial point is this force can be written as sum of the internal forces acting on particle plus external forces acting on the particle. Okay, so let's suppose that F1 bar is equal to F1 internal plus this is F1 internal plus F1 external. Okay, similarly we can write for second particle it is R2 bar cross F2 internal, so the force acting on second particle, the internal force, all internal forces acting on second particle plus sum of all external forces acting on second particle, so that will be F2 internal plus F2 external. Okay, so I am not going to write it for each and every particle, I will just write for last particle, so it is Rn bar crossed with Fn external plus Fn internal. Okay, Fn internal plus Fn external. And then now what we can do is we can rewrite this, so we can split the internal and external forces. So I can write this dl bar by dt equals to R1 bar crossed with F1 internal plus for second particle it will be R2 bar crossed with F2 internal plus so on and so forth up to plus. For nth particle, it is Rn bar crossed with Fn internal. So I have taken cross product of this R1 bar with first term. So first term in all these terms of all these terms. Next, what is left there? It is R1 bar cross F1 external and so on and so forth. So we'll write that. So we have plus R1 bar crossed with F1 external plus so on and so forth up to plus Rn bar crossed with Fn external. Okay, and now 5 we have done this. So what we will do is we will call this term, so R1 bar crossed with internal force acting on first particle, as the torque acting on the first particle due to internal forces. Okay, so R1 bar, the cross product of position vector of particle with internal force acting on a particle, I am going to call it the torque, internal torque acting on the particle. Okay, so this is internal torque acting on first particle, so I will call it Tau1 internal plus internal torque acting on second particle plus so on and so forth up to plus internal torque acting on nth particle. All right, so this term will be my total internal torque acting on the body, because I have taken sum of internal torque due to all internal forces. Okay, torque due to all internal forces acting on all particles, plus here we have external torque acting on first particle plus so on and so forth up to plus external torque acting on nth particle. All right, and now what happens is, so again I will erase this part. All right, so now what happens is this internal torque becomes 0. Okay, so let me explain this, why this happens. So let's consider this body. Okay, this is origin, and let's consider any two particles. So let's suppose these are two particles. So internal forces can be anything. So now the internal forces between these two particles, they will act along this line. Okay, the line joining the two particles. Okay, the forces can be actually contact forces or non-contact forces. So we have talked about contact forces and non-contact forces before. So whatever it is, the contact force or non-contact force, it acts along the line joining the two particles. Okay, so let's suppose this is particle number 1, its mass is m1. This is particle number 2, its mass is m2. Then the force due to m1 on m2 will act along this line like this, and force due to m2 on m1 will act like this. Okay, in this direction. So let's call this F21, this is F12. And if you think in terms of the position vectors, then so if you consider this point as an origin, then position vector is R2, position vector of this particle is R2, and this force is F21. So if you take the cross product of the position vector with this force, with this internal force acting on this particle due to this particle, then what will be that cross product? It will be 0, because cross product is the magnitude of cross product, it is magnitude of first vector into magnitude of second vector into f21 multiplied by sine of the angle between those two vectors, and angle between r2 and f21 is 0. Okay, and that's why this term will become 0. So here what we have done is we have considered only two particles. So likewise we can find out force acting on this particle due to all particles within the body. Okay, and we can calculate the torque due to all such internal forces, and if you think, this torque will come out to be 0. Okay, so this internal torque vanishes, and therefore I can write dl bar by dt. So rate of change of angular momentum with respect to time for a body, it is not just the total torque acting on body, it is just the total external torque acting on the body. Okay, so it's going to be total external torque, which is sum of external torques or torques due to external forces acting on each and every particle. So sum of all those external torques will be total external torque acting on the body. So rate of change of angular momentum with respect to time is equal to total external torque acting on a body. All right, so is this thing clear? Please tell me. Okay, so here comes the law of conservation of angular momentum for rigid bodies. So for a rigid body, the angular momentum of rigid body remains conserved in absence of external torque acting on the body. So what that means is, if external torque is equal to 0, then change in angular momentum with respect to time will be 0, and that means I can say if change in this quantity is 0, that means this quantity remains constant or conserved. So this is the law of conservation of angular momentum for a rigid body. Okay, so the angular momentum of a rigid body remains conserved in absence of external torque acting on a body. All right, so hope you understood this. Okay, then next what we are going to do is what we will do is we'll talk about work done and energy in case of rotational motion. Okay, so work done and kinetic energy in rotational motion. So now once again let's let's go back to the case of single particle. So once I'm sorry. So let's go back to the case of single particle. So let's suppose we have this particle which is performing circular motion, okay, so about this axis, and in some time the particle goes from, let's say, this point to some other point, let's say this point, okay. So this is its position vector at time t, this is r bar at time t, this is position vector at t plus some later time, let's say delta t. So this is r bar at t, this is r bar at t plus delta t. So how much is the displacement? So of course this vector here is the displacement vector, so let's call it ds bar, okay. So I will write it here, ds bar, okay, it is this vector. So now displacement vector ds bar can be written as r bar at t plus delta t minus r bar at time t, okay. And in this time, so from t to t plus delta t, the time interval is delta t. So in time delta t, suppose delta theta is angular displacement of the body, okay, or this particle. So this is angular displacement, it is, let's say, delta theta, it is this angle over here, okay. So if I am calling this ds, I will call this d theta, not delta theta. So this is d theta. All right. So now suppose there is some force acting on this particle. So the force is F bar. So how much is the work done by this force on this particle? Okay. So we know work done is dot product of force and displacement. So if this time interval is very small, so we can say the angle between force and displacement is this one. Let's call this angle alpha. So what is the what is the work done? In time dt, so it is dw. So dw is just dot product of this force F bar and displacement. So displacement is ds bar, and it can be written as F bar, the magnitude of F bar into magnitude of displacement ds multiplied by cos of the angle between the two. Okay, so this angle here it is alpha, so cosine of alpha. All right, and then now if we talk about this angle, so this is precisely the angle between position vector of particle at time t and the force. Okay, so force is acting in this direction, position vector, it is directed in this direction. So I will call this angle theta. So theta is angle between the position vector and force. Okay, so now cos of alpha will be sine of theta, because alpha and theta are complementary angles. Okay, so sum of alpha and theta is 90 degree. So cos of one is sine of other and sine of one is cosine of other. Okay, So this thing can be written as f into ds multiplied by sine of theta. Alright, and now what I will do is I will represent this ds in terms of r and theta. So we know that I will write it here only. So angle is the displacement divided by radius, or you can say arc divided by radius. So it is arc upon radius. So this angle d theta can be written as what? It can be written as this arc length ds divided by radius r. Okay, so radius at time t. So d theta equals to arc length ds divided by r, and I can substitute it over here. So I get dw equals to f into ds can be written as what? So ds can be written as r times d theta. Okay, so r into d theta multiplied by, we have sine theta, and if I multiply f with r, so it can be written as the magnitude of torque. Okay, so since I will erase this. So we know torque acting on a particle is cross product of its position vector with force. So magnitude of torque is just magnitude of this first vector into magnitude of second vector multiplied by the sine of the angle between two vectors. Okay, so we have all those things over here. So r, f, and we have sine theta. So theta is angle between r and f. So I can represent this term f, r, and sine theta as magnitude of the torque. So dw can be written as what? It can be written as, all of these give me torque acting on this particle due to this force. So it is tau times d theta, and we got the formula for formula for work in case of rotational motion, which is analogous to the formula for work in case of linear motion. So in linear motion we have this formula, dw equals to f times ds. Analogous quantity of force in rotational motion is torque. Analogous quantity of displacement is angular displacement. So we got this formula, dw equals to tau times d theta. Okay, is it clear? Yes. Is this thing clear? All right, good. So now, okay, so now we have defined power. So in chapter work, energy and power, we had defined power. So power is rate of change of rate of doing work. Okay, so here also I will define power. So power in case of rotational motion is also, definition of power is same, it is dw by dt. Okay, rate of change of work with respect to time. So if I do that, what do I get? In place of dw I will write tau d theta. So I have tau d theta by dt. And what is d theta by dt? So d theta by dt is omega, rate of change of angular velocity with respect to time. Rate of change of angular displacement with respect to time is angular velocity. So we have power in case of rotational motion as tau multiplied by omega. And again you can see it is analogous to power in case of linear motion. So in case of linear motion we had studied that power is dot product of force and linear velocity. So again you can have an analogy. So analogous quantity of force in rotational motion is torque. Analogous quantity of velocity is angular velocity. So power changes to what? Tau times omega. So this is power for a rotating body. Okay. So then now we have talked about the work done by torque in displacing a body by angle d theta. Now let's talk about the change in energy. Okay, so here any torque acting on this particle, it will only change what? Its kinetic energy, because there is no potential involved over here. Okay, so it will only change the kinetic energy of body, and therefore we can say that torque acting on a body increases its kinetic energy. Okay, yeah, and we can generalize this formula for rigid body. This was for a single particle, so for one particle it is tau times d theta. For rigid body it will be what? Sum of the torques acting on all particles, so tau 1 plus tau 2 plus tau 3, so on and so forth, up to plus tau n. So for rigid body this formula can be written as dw can be written as all particles of body will rotate by angle d theta, so it's only the torque that will change. So it is tau 1 times d theta plus tau 2 times d theta, work done on first particle, work done on second particle. So we have done this many times in this chapter. So, or let me write explicitly, tau 1 times d theta plus tau 2 times d theta plus so on and so forth up to plus tau n times d theta, and we can take d theta common, so it is just tau 1 plus tau 2 plus so on and so forth tau n times d theta. So this is just the total external torque acting on body multiplied by d theta. Okay, so tau times d theta. So total work done. So work done on a rigid body is just sum of work done on all particles of rigid body. So it is just tau times d theta. Alright, so formula remains same. Okay. Yeah, is it clear? Yes. Okay, so we have done nothing actually. What we have done is, this was for one particle. For case of rigid body, there will be n number of particles within the body, and total work done will be equal to what? Work done on first particle plus work done on second particle plus so on and so forth. Okay, up to plus work done on nth particle, and these are work done. So tau 1 times d theta plus tau 2 times d theta we can take common. So we are left with tau 1 plus tau 2 up to tau n. So it is just total torque acting on body. Alright, so yes, it is clear. So we can move ahead and we can find out the increase in kinetic energy. So increment in kinetic energy of rotating body. Okay, or rate of change of kinetic energy of rotating body. So kinetic energy of rotating body is given by formula half of I omega squared. This we have studied in, I guess, last class when we defined moment of inertia. So here I is moment of inertia of body, omega is its angular velocity. And just to recall, what is moment of inertia? So if there are n number of particles in the body, all those particles perform rotational motion with same angular velocity. So for this particle, if this is distance of this particle from axis of rotation, so let's call this particle, first particle, its mass is m1, this is distance from axis of rotation, then its moment of inertia is given by m1 r1 squared. Okay, so moment of inertia of body I is equal to sum of mi ri squared. So it is m1 r1 squared plus m2 r2 squared, so on and so forth. So this I changes from 1 to n. Summation of mi ri squared is moment of inertia of a body. Okay, and kinetic energy of body, rotating body, it is given by this formula, this I multiplied by omega squared, where omega is its kinetic energy. So now what will be rate of change in Ke, in kinetic energy of rigid body? So it is dk by dt. Okay, and this half remains same, I remains same. So I am taking derivative of this term with respect to time. So on right hand side, again I will take derivative with respect to time. So let me just write, it is d by dt of this term, half of I times omega squared, out of which half and I are constants, so we can take them outside. So let's take them outside. So half of I have taken outside, so it is derivative of omega square with respect to time. Okay, and here we have to use chain rule. So chain rule of derivatives that we had studied in, I guess, third chapter. So what is derivative of omega square with respect to t? So let's suppose this term is f of omega, it is omega square. I am just briefing the chain rule. So derivative of this function with respect to time will be derivative of this function with respect to its argument is omega, okay, or it is function of omega, so its derivative with respect to omega multiplied by derivative of omega with respect to t. So what we can say is we are just multiplying and dividing by d omega. I am taking df by dt, okay, and f is omega squared, whatever it is, df by dt is df by d omega multiplied by d omega by dt. Okay, so I am just multiplying and dividing by d omega. Okay, so what is df by d omega? So it is derivative of this f of omega, so derivative of omega square with respect to omega. So now this is function of omega only multiplied by d omega by dt. So what is this? Rate of change of angular velocity with respect to time is angular acceleration. Okay, and this derivative is simple. What is derivative of x square with respect to x? It is 2x. So just like that, derivative of omega square with respect to omega is 2 times omega. So we got this derivative, so it is 2 times omega multiplied by alpha. Okay, and then I will erase this and write dk by dt. So dk by dt is this thing. We had half of I over there, if you remember, multiplied by 2 times of omega into alpha. 2 and 2 gets cancelled out. And what is I times omega? So we have proved this in last class. This is the torque. Okay. So this is okay, or sorry, this is angular momentum, not torque. Okay, let me keep this as it is. So it is I times omega times alpha. And tell me if it is clear till this point. Okay. Is it clear? All right. So now what we can do is we can compare power which we got from rate of change of work and what is rate of change of kinetic energy with respect to time. So again, it is power. Power is rate of change of work, rate of doing work, or rate of increment in energy of a body. So this is another definition of power. Okay, so this is another definition of power. And if I just call this formula 1, this equation I will call 2. So if we just compare 1 and 2, what do we get? So what we get is so from 1 and 2, what I can write is 1 is tau omega equals to I into omega into alpha, and this omega gets cancelled out and we are left with tau equals to I times alpha. So this is another formula for torque. Okay, so torque is rate of change of the angular momentum with respect to time. We had found this formula, tau equals to what? dl by dt, and tau is again I alpha, I times alpha. So we got this two formulae. Okay, and now what we can do is, if you want, if you like, you can compare these two formulae. So I can write that dl by dt equals to I times alpha. Okay, so this thing is constant and this is derivative of something with respect to t. So this can be written as I times d omega by dt. So this is dl by dt, and since this term is constant, I can put it outside. So it can be written as d by dt of I omega, and therefore I can write L is equal to I omega. Okay, so just by comparing the terms, I can write L equals to I omega. Alright, so actually we had proved this for the case of single particle. For rigid body, I can write it like this. Okay, so is it clear? Alright, so now what I will do is, so now we have completed our analogy between linear motion and rotational motion. So I will just put everything in place. So let's check this whether this doesn't work. All right, so now I will write quantities in linear motion and the rotational analogs. So quantities in rotational motion. So this is good thing in this chapter, we don't have to remember anything and we can write everything from analogy. So let's write the linear displacement. It is denoted by S. And what is its rotational analog? So rotational analog is angular displacement. I will just write disk, it is theta. Okay, linear velocity is V, which is ds by dt. Okay, or if you take x, then it is dx by dt, and angular velocity is omega, which is d theta by dt. Okay, similarly, then linear acceleration is dv by dt, rate of change of linear velocity with respect to time. Angular acceleration alpha is d omega by dt. Okay, so this is for the kinematics. For dynamics, we have quantity which determines inertia of linear motion. So inertia is given by mass, and in rotational motion, moment of inertia I, which is summation of I goes from 1 to n of mi ri squared, it defines the inertia of rotational motion. Okay, then next. So next we have force. So we have Newton's second law. Which tells us force is dp by dt, rate of change of linear momentum with respect to time. So analogous quantity of force in case of rotational motion is torque. So Newton's second law in case of rotational motion becomes tau equals to dl by dt. Okay, and what is tau and L? So torque is r bar cross f bar, moment of force, and L bar is r bar cross p bar, moment of linear momentum. Okay, then next, okay, before that we have another statement of Newton's second law. So F equals to mass times acceleration. So similarly here we can write torque equals to analogous quantity of mass is I, moment of inertia, and analogous quantity of A, acceleration, is alpha. Okay, then so this is for Newton's second law. Then what about power? So we don't have to remember it. It is dot product of analogous quantity of force and analogous quantity of velocity. So it is dot product of tau and omega. The last is kinetic energy. K is half of mv square, half of kinetic energy is half of I times omega squared. Okay, there is one more formula, work done. Here dw is f dot ds, and what is work done over here? So I hope you can see this. Yes. Okay, so here I will write work done is tau times d theta. Okay, so that's that. All right, so now we have to memorize this chart for this chapter, and actually we don't have to memorize because everything comes by analogy. Okay, so but you need to memorize a chart for moment of inertia. Okay, so all right, then is it clear? Yes, hi Sandeep. So if it is clear, let's stop at this point. All right, then we'll stop at this point, and in next class we'll discuss something. Okay. Okay, in next class we will discuss the equilibrium in rotational motion. So I will stop here. Bye.